Okay, let's start this video. First, let us see the contents. First, I will introduce the wavelet transform based denoising scheme. Then I will explain some threshold estimation methods. And then I will explain the two important Matlab functions for use for denoising. One is the wden, other is the wdenoise. And then I will show you some example codes for denoising in Matlab, and then I will show the denoising examples in Simulink. Before going ahead, I recommend you to watch my previous video, which is based on the wavelet transform theory and its applications. Link is given in the description. It is important actually to go through this video because it will give you the theoretical input to understand this video in better way. Let's see some preliminary theory. The noise model. When a signal is transmitted over some distance, it is frequently contaminated by the noise. Here the noise is a random signal which definitely causes some undesired changes in the original signal. The simplest model for acquisition of noise here used is the additive noise. So you can see that the contaminated signal f dash k is equal to the original signal fk plus noise signal nk. There are different kinds of noises. For example, the white noise, pink, blue, impulse noise, etc. For this particular video, I am taking the example of only the white Gaussian noise with a zero mean value. And we are assuming that noise is additive and noise is a high frequency random signal. So here our objective is to remove noise nk from the noisy audio signal f-k using the wavelet transform based techniques. So this is my wavelet based denoising scheme. Here you can see that the signal fk is first decomposed using the discrete wavelet transform in various labels, and then we get the coefficients at these labels. We get detail coefficients and approximation coefficients. All those coefficients, detail coefficients only, are thresholded. I mean, they are shrinked, and then these modified wavelet coefficients are collected together, and we take the inverse discrete wavelet transform to achieve the signal back, which is our denoise signal. Here in the thresholding, how to actually set the thresholds. To set the thresholds, there are certain noise estimation methods by which we find the appropriate threshold values. So let's see what are those. We have some noise estimation methods like minimax criterion, square root log, which is known as the universal threshold. It is the most popular method. And then Sure method, which is a Steen unbiased risk estimate. It has two forms, regress and heuristic. And then Bayes method, and then block.js, and then false discovery rate FDR. Here these are the Matlab functions which support these types of noise estimation methods. So for example, the wden support the first four, while the wdenoise support all of these. But in wdenoise, the regress sure and heuristic sure are combined together as only sure. This wden command is actually the older command, and while the wdenoise is a newer command which is available in the newer releases of Matlab. This is the square root log criterion for threshold estimation, which is also known as universal threshold method. It was given by the Donohoe and Silverman, and the formula is this. So lambda j, which is the threshold value, is given by sigma j square root log 2 log nj, where nj is the length of noisy signal at the jth scale, I mean the jth decomposition label, and sigma is the median absolute deviation, which is in short known as the MAD at the j scale, which is given by the MADj upon 0.6745, where MADj is the median of all the wavelet coefficients at scale j. So it's easy one. And these are actually the thresholding method, that how the wavelet coefficients are shrinked. We have the major two types, hard and soft thresholding. In the hard thresholding, you can see from this figure that all input wavelet coefficients Ci, which are lying in the range minus lambda to plus lambda, are neglected, zeroed out, while the coefficients beyond the lambda plus minus, they are taken as it is. So the output coefficient C0 is equal to Ci beyond the lambda. But in soft thresholding, the wavelet coefficients between minus lambda and plus lambda, of course they are also zeroed out, neglected, but beyond the minus lambda and plus lambda, they are also reduced linearly as shown here. And there are other methods also for thresholding. I am not discussing here. Let's see the wden Matlab function. So this is the syntax of wden. XD is your output signal, X is your noisy input signal, TPTR. This represents the threshold estimation method. As I explained in the previous table, wden supports rigorous shear, heuristic shear, and square root log and min-max. And for S or H, in this place you can write either H or S, representing soft or hard thresholding, and then SCL, scale. For this variable, you will write either 1, either SLN or MLN. If you write 1, then there will be no rescaling to estimate the noise level. And if you write SLN, then it will be the label independent thresholding. And if you write MLN, then it will be known as a label dependent threshold estimation. That means for SLN, only a single lambda will be found out for all labels, while if you choose MLN, then for each label the different lambdas will be calculated. And N is the number of decomposition level, and the W name is the name of wavelet which will be used. So let's see one MATLAB example. Here I'm using a MATLAB inbuilt noisy data, which you can load like this, wdenoise data. Actually this data is in time table format, so first convert this into array using table to array, and it has actually 10 columns. So just taking the first column as a noisy signal, so xn equal to xn all rows and only the first column, and then passing this noisy data into the wden Matlab denoising function. So this xn is noisy signal, square root log, it is your universal threshold, noise estimation method as represents soft thresholding, MLN represent the multi-level label dependent thresholding, 5 represent number of wavelet decomposition levels, and sim8 representing the wavelet used, which is a simlet 8. And these are few plot commands. So let's see what will be the output of this program in MATLAB. This program I have already written in MATLAB, so I will simply press this run button to execute it. Let me execute it. Okay, this is the output which we achieve from this piece of code. You can clearly see that how the wavelet based denoising works perfectly. You can see the blue one is your noisy data, and this red one is your filtered output data. So let's come back to another example. Another function which is used in MATLAB is the wdenoise, which is the newer function, and this is the syntax which is given as here xd is output signal, x is your input signal. Now denoising method, as you can see in wden also, where it was the tptr, here it is denoising method. So you can have base, you can have shear, you can have square root log, and others which are supported by the wdenoise. Here they are written here, like base, which is the default, block.js, fdr, min, max, shear, and universal threshold. And the threshold rule, for threshold rule you can choose the soft thresholding, hard, thresholding, mean, median, and James-Stein. Then noise estimate, either it is label dependent, which is equivalent to the MLN in wden, and this is label independent, which is default, which is equivalent to the SLN of wden. And then label is the number of wavelet decomposition, and the wavelet name here we have used a SIM4. SIM4 is actually the default Simlet 4. You can give other wavelets also. So let's see the Matlab example. This is the Matlab code to see the wdenoise function. Here again I have used the Matlab inbuilt noisy data, which is the noise top. So I'm loading it and then passing this noisy signal in wdenoise. So here I am only passing the signal. I am not giving any other parameters. So it means all the default values will be taken. So you can see in the previous syntax, everything will be default, like the denoising method will be base, and then thresholding rule will be soft, and it will be the label independent sort of things. So it will be denoise using all default values, and then these are some plot commands. So let's see what type of output I get in Matlab. So this program I have already written. Let me execute it. Okay, so this output I achieve. Again, you can see the very impressive output, which is the red one for this blue noisy data. So that's the strength of Wavelet. And now let me jump to the another information. Okay, now I'm taking the example of audio signal denoising with help of wden Matlab function. So here I will show you that how you can denoise a noisy audio using wden. So the first line of this Matlab is UI get file. Actually, it helps you to choose or select your audio file. Then that all audio samples will come in X, and the sampling rate will come in Fs by this audio read function. And since this audio is not corrupted by the noise, so I'm adding some white Gaussian noise to this signal. So you can see that AWGN adds some white Gaussian noise to this original signal X. So Xn becomes your noisy signal, and then passing this noising signal to the wden function. So here I'm using the square root log, again universal threshold estimation method, soft thresholding, and then label dependent thresholding, and then a number of decomposition levels are 3, and then Simlet 8 wavelet is used, and these are few plot commands. So let's see what output I achieve in Matlab. So I have already written this program in Matlab. Let me execute it. So it will ask me to choose my audio file. So I'm choosing this flute. It's an MP3 file of 10 seconds. Open. Okay, I get this output. So blue one is your original flute signal, and red is the noisy signal. So you can see the clear difference between blue and red. And this green one is your output, which is denoise. It's filtered using the wavelet. So this is your output. You can clearly see that this blue is most matching maximum with this green one, but the clear picture I will receive only if I listen the song, the noisy version as well as the denoise version. Then it can give me whether that how the wavelets are doing actually. So you can see that the sampling rate Fs is 44.1 kilohertz. So let me use a sound command to listen the signal. So first I am listening the noisy one, right? I am listening the noisy one. So Xn was the noisy signal. So now listen carefully. Okay, so you could easily listen that there is a lot of hissing background noise. So now let me play the denoised signal, which is wden, and let's see the strength of wavelet. Okay, so you could clearly listen that how the noise is really removed from accent using the wavelet. So this output is much better than that noisy input. So let me come back to my presentation and see the example, the same example with the wdenoise function. So again, I will denoise the same audio using this wdenoise, which is the newer function of the Matlab. And here you can see that the denoising method, I'm using base, threshold rule is the soft, and noise estimation level is the noise level. It is level independent, and a number of decomposition labels, I'm using 8, and the wavelet is the Simulink. So let me execute this. So this program is written already. Let me press the run button. Let me choose the audio file. Okay, so this is the output. You can see the blue is your original signal, red is the noisy, and this green is your filtered output. And let me listen again these in Matlab using the sound command, so we can have the clear picture. So first we will listen the noisy one. Okay, now let me listen the output. Okay, so you can clearly differentiate between input and output. Okay, now I will show you the denoising of audio signals using Simulink. So I have made a Simulink model, so that will perform the same operation which we have seen with those Matlab codes. It will also use the wavelet transform to denoise your audio signal. So here you can see that we have few blocks. So from multimedia file and this dyadic analysis filter bank and then dyadic synthesis filter bank IDWT, these are all from DSP system toolbox. You can find array plot and audio device writer. Audio device writer is also in audio system toolbox. From multimedia file is also in audio system toolbox. And then these two blocks, delay alignment and thresholding, these two actually are the subsystems which are not directly available in the Simulink. We have to create. So this delay alignment is created with the delay elements, while the thresholding is created with the dead zone elements elemental block which are available in Simulink, right? But here this is easy, everybody can make it, but the question is that how to find the thresholding values for each label for this noisy flute.m4a file. This is a noisy data. So question is that how we can find the threshold values. Yes, we can find the threshold values. We have to find it manually right now for this model. So these threshold values we can find by executing this wden command with these output parameters. So output is xden cl n thr, and then xn is your input noisy data. For example, that noisy flute.m4a, first you have to read that in Matlab using audio read, then pass it to the wden function. Then you can define the square root log method, soft thresholding, label dependent, and 3 number of decomposition labels, and Simulink 8 I'm using. So once you execute this in Matlab, you will find all the threshold values related to all according to all the decomposition label. So you can see that in THR. Here in this command, if you use mln, then you will find thr will include different lambdas for each level, and if you write the sln, then thr will return only a single value which will be used for all decomposition levels. So let me see that how I can find these thr in MATLAB. So this command I have already written, just executing by pressing it. So I have executed it. So all threshold values are now stored in thr. So let me see what I get inside thr. So these are the three threshold values: 0.1297, 0.1297, 0.1406, etc. So when copy these values and pass these values to your Simulink block. Okay, so in the Simulink block, open it and enter those thresholding values for each level. I will show you in the Simulink also. So let me jump to the Simulink. So this model I have already made to save the time. This is your input block. So when you double click it, you can choose any of your file, any audio signal. You just press browse button and you can choose your audio file. So I have chosen a noisy flute, which you have already listened in the previous examples. So it's a 44.1 kilohertz sampled 128 kpbs. It's a mono sound, and this is a direct analysis filter. When you double click it, you get this direct box. You can choose wavelets from this list. So if you do not want to change similars, you can choose hard, Derbyshire, square flats, bi-orthogonal, etc. And then you can wavelet order and then number of decomposition level. Keep all other things as it is, and now open this dynamic synthesis and be sure that the wavelet which you have used for analysis, the same should be used for synthesis. So Simlet 8 is used for both analysis and synthesis, otherwise there will be error. And now let's see the thresholding. So since it's a subsystem, it is made by other blocks. So when you double click it, you can see these four tiny blocks which are the dead zone. These are the fundamental blocks which you can find from Simulink in commonly used blocks. So when you double click it, you get those values. That means you can define here the minus lambda and the plus lambda. That means minus values of your threshold and the plus value of your threshold. So this is your four blocks represent the soft thresholding, and for second one and for third one and the last one, the thresholding is 0 because the last one is actually the approximation coefficients. These are not detail coefficients. So the first three are the detail coefficients, the CD1, CD2, CD3, and this is your CA3. So in denoising, approximation coefficients are left unchanged. They are not shrinked. Only the detail coefficients are thresholded, right? And in delay alignment, let's see what is inside delay alignment. We have the simple delay blocks that you can find from DSP system toolbox or from this Simulink toolbox also. This is actually necessary because the decomposition at every level takes some time, so it introduces some delay. So if there are three levels of decomposition, that means the signal after the third decomposition level, we get CA3 approximation coefficients and CD3 detail coefficients in the last, after the three number of delays, while the signals at the first level CA1 and CD1 we get earlier. So there is a mismatch in the time. So to match all those signals in time, this delay is introduced. So at the input ports, the signals are coming in different times, while at the output ports all signals are we are getting at the almost same time. So here you can see that the first block has a 3 times delay of the second, because we are using a 3-level decomposition. So if you are going for more, they will be adjusted accordingly. And the last two, they don't have any delay box because we signal 3 and 4 we are getting after the third decomposition. So we are getting them in the last. So let me execute this and see what is the output. So I'm pressing this green button. This was actually the output, which is the denoise. The noisy one you have already listened in the previous, where we have the lots of background hissing noise. So in this output, that background hissing is almost removed. So let me come back to the presentation. Now there is a problem with this model. The problem is that this model becomes input dependent. Why? Because the threshold values which we have written in this thresholding block, they are found by this wden command, where the input noisy fluid was passed as xn. So once you change this input, obviously the threshold values will be changed. So all threshold values depend on the input. So once you change the input, your threshold values will automatically change. So every time you have to execute this wden command to find the new thr values and then updating the thresholding block. So it is somewhat irritating. So can we make a model where we do not require any manual editing or updating those threshold values in these threshold block? So we can make input independent block. Yes, we can. So this is the model, which is hassle free. There is no need to find manually these threshold values. This model will automatically find all the threshold values depending on the input, and then automatically threshold those detail coefficients. So what I have used here, I have used these Simulink user defined function blocks. So you can write your own code inside these block. So it is simple. I will show you that in Simulink. And I have written these two functions. This first block is actually used to find the threshold. So thselect is the Matlab inbuilt function which is used here. It for the input x, using the square root log method. That means you can give here other methods also, like min max or sure method. Here I have used the universal threshold method. So with help of this threshold method, this function finds the appropriate threshold level, right? So this found threshold thr value is given to these three blocks, which are actually your thresholding blocks. They will shrink your or adjust the wavelet coefficients of input. So inside these blocks, I have used the wthresh function. So it can threshold the input x, input array x, using soft thresholding. You can write h also, and with the given thr value. So this model becomes input independent. So you can freely choose any input audio file. This block will automatically find the thr value and will supply these thr values, threshold values, to all these three threshold thresholding blocks. But the problem is here that this model calculates a single threshold. That means it works on the level independent model, which is equivalent to the sln of wden function. So the threshold value is calculated on the basis of the CD1, that means the detail coefficients of level 1. You can modify this model into your MLN framework, that means a multi-level decomposition. So for that case, instead of this one block, you need to provide two more blocks, one for CD1, other for CD2, and other for CD3. So there will be three blocks calculating the three THR, THR1, THR2, THR3, and then supplying the separately to these blocks. So this is not a big deal. You can make it that multi-level thresholding model. So let me see that how it performs in Matlab. So let me press execute button. Okay, you could clearly listen that how beautiful output we are getting from this scheme. So you can choose any input. So it is input dependent model. Let me come back to the presentation. Okay, there is a Matlab application which is already there, which can be used directly for denoising. So that is that you can find in Matlab application tab. So open the Matlab and go to the apps tab and then expand it and go to the signal processing area. Okay, this is your signal processing and communication area, and here you can see that this is your Wavelet Signal Denoiser app. So you can press it and you will get this window. Here you can import your audio signal, so you can load signal, and then xn is which is already lying here in our workspace, which is your noisy signal. So you can take it and just import it, and it will do automatically denoise with all default values first. Later you can change those values as per your requirement. Okay, this is the output which you will get. You can see that blue one is your noisy signal and this orange brownish is your output. And here you can see the details. Let me enlarge it. You can see that Wavelet uses SIM4, number of decomposition labels are 15, denoising method is a base, thresholding rule is median, and level independent thresholding is used. So if you want to change all these details, yes, you can do. Press this wavelet tab and you can choose your any wavelet. For example, let me choose a Koi 5 and method, let me universal threshold, and level of decomposition, let me choose 5, and this is the soft thresholding. And you want to use level independent or level dependent, let me choose level dependent, and simply press this denoise button and it will denoise for you. Okay, this is the output which you get from your own with your own parameters. So you can see the details are Koi 5, level 5, universal threshold, all of details are here which you have given, and we get this outputs. Now if you want to take this output back to the workspace, you can really do this. Simply press this export button, and then you have the two options: export denoise signal, it will export to your workspace, or generate Matlab script. So if you want to press this generate Matlab script, it will write a Matlab code for you. So it writes that wdenoise functions with all chosen parameters, right? So that's another very useful application. So with this application, you can do some experiments for a study point of view. So that's it for this video. I really thank you all for watching this video.